Okay, so officially welcome you all to this course, Mixed Signal IC Design, right? So as per the convention, so let me first give an introduction and motivation to this course, right? And I mean the course title is Mixed Signal, right? So what do you think it is meant by mixed signals? Yeah, basically that, right? I mean, to give a broad introduction, I mean, if you take any signal it represents any physical quantity. Usually the deal is we convert any kind of signal to electrical signals like voltages or currents, simply because you can easily process electrical signals, right? I mean, you can't add two temperatures, but you can add two currents easily, and that's why we have all these sensors for, right? And if you take, let us say, some voltage signal like this, so with time it's going to vary. So let's say it does something like this. So the information here is contained in time or in amplitude? Amplitude. Okay, so then I can have another signal which has same amplitudes but stretched in time, no? Is it the same signal? So where is the information contained? That's what, if the information is only in the amplitude, I can have a similar signal with the same amplitudes but stretched out like this, but that's not the original signal, right? It's both in time and amplitude. Okay, so if you take any signal, you need to make sure you know what the signal level is at different time instance, right? Because we need both these things. So this is time and amplitude, and the the signals we encounter in the real world, they exist for all possible values of time, and similarly they can take any value in this y-axis, and they are basically the continuous time and continuous amplitude signals, as you know, and they are the analog signals, right? But of course, if you want to store such an analog signal, you will in principle have to save its value for all possible values of time, right? Of course that's not possible. So what do you do? So yeah, basically you try to save its information at discrete time instance, say like this, right? And usually we make sure these time periods are uniformly spaced, so which means you don't need to save the timing information separately, right? Because the moment I know what rate at which I have strobed the signal, I simply know the time instance also. Similarly, in the y-axis, instead of saving all possible amplitudes, I'll take a range of amplitudes. I'll say any amplitude within this range, I'll round it off to some other amplitude within here, say here. I'll do it for all amplitude ranges. So then I'll end up with the finite number of amplitude levels to store, and this it can encode using binary bits, and this what gives you your discrete amplitude and discrete time, discrete amplitude signals, which is the digital signal, as you know, right? And of course, to convert from this analog to digital, you can do in two ways. You can either first discretize the time and get a discrete time continuous amplitude signal. And what is this process of discretizing the time axis called? Sampling. I'm sure everyone is aware of that. And once you discretize the time axis, you can go ahead and discretize the amplitude axis. And what is this called? Yeah, I'm sure you would have heard this term in some form of the other. I mean, the other way is to first discretize the amplitude axis. That will basically give you a continuous time discrete amplitude signal, and then you can go ahead and do this. Mathematically, you can do anything, right? You can first sample and quantize, or quantize and sample. But of course, in practice, it's much easier to sample first and quantize later. That's all. Yes. That is much easier to do in practice, so that's what it's done. Okay. In most cases, that is what is done, at least. Right, and of course, again, you'll also want to convert from digital to analog, so you can do something similar. And these circuits, which basically deal with conversion of signals from one domain to the other, they are called data converters. Right, and of course, the one that converts analog to digital, I'm sure you know, it's called analog to digital converter, ADC. and this is the symbol for the ADC. Okay. I mean, the deal is, so analog signal is the input, so it's just single channel, so one line. Output is digital, so we'll have a fat line pointing there is multiple digital bits there. Similarly for the DAC is a digital to analog converter. It's a symbol. Great. So now we have established what will be the focus of this course. The next question is, okay, what is the practical relevance of this? Now again, as with any circuit design course, to give a practical example of or practical application of any circuit, what is the best example for application of circuits? You might have heard in multiple classes, right, in circuit design course. What is the best real life practical example you all have in your pockets? Smartphones. Okay. I mean, and even before that, as a live example, right? I mean, this lecture is right now being recorded in my tablet. It's going to get uploaded to the cloud or something, and it's all strings of ones and zeros. But what I'm speaking is an analog signal, right? So obviously here there is an ADC that is in between, digitizing what is being spoken and storing it. Similarly, when you are playing it back on your smartphone or laptop, you will have a DAC, right? And of course, your smartphone is much more smarter than this. It has more features, and I will call it as a warehouse of radio transceivers. And if you take a radio transmitter, I mean, are you guys aware of how many of you have taken some course on digital modulation or aware of digital modulation? Okay. Or even if not, it's okay. See, if you take any transmitter, all modulation now it all happens in the digital domain. So this is a digital modulator. But the signals you might want to transmit, they most likely will be analog signals. So what do? You first have to have an ADC to convert it, and then you do the modulation. And of course, you can't directly transmit the digital signal, so you'll have to convert it to an analog signal. And then you upconvert it in frequency, and then directly transmit it. Of course, in practice, there are a whole lot of other blocks in between to make this functional, but the bare essentials of any radio transmitter are these. Okay. Again, if you look at the mobile receiver, to receive the signals, you need to have an antenna. And now your antenna is not going to receive the required signal alone. It's going to pick up all sorts of stray signals everywhere. So how do you get only this part from the signal? You'll have to do some kind of filtering. Yeah, it's a bandpass filter, so you'll have some filtering here. And once it's filtered, you again down convert it. You digitize the signal and demodulate. Okay, this is demodulated. Okay. And as you will see later, I mean, this down conversion can also be combined as a part of the ADC. So in principle, again, the bare essentials here are an antenna, filter, and an ADC. Okay. Again, as of now, we need more blocks in between to make this a functional receiver. But these are the bare essentials. And the point I'm trying to get at is, in a radio transceiver, data converters play an essential role, right? And your mobile phone has a whole bunch of them, like say one for Wi-Fi, GPS, Bluetooth, NFC, and multiple standards, right? 2G, 3G, 4G, 5G, and whatever you have. And not just that, when you have your touchscreen, your touchscreens are all capacitive touch, right? And again, loosely speaking, it's like a crossbar structure like this. And the idea is, whenever you make a touch, the capacitance around that location is going to change, right? Because the chambers are going to move, and because of the capacitance is going to change, and the change in the capacitance is what is sensed to detect if the touch is made or not. And how much the capacitance changes determines the sensitivity of the touch, right? You have this pressure sensitivity nowadays. So it is not just enough to say if the capacitance changes, you also need to know how much the capacitance has changed. And again, for sensing this, you have an ADC here. So if you have your touchscreen controller, it's again going to have a whole bunch of ADCs. Okay. And I mean, other example is, I mean, all this, gigabit Ethernet, or in your phone USB Type C. You had old Type A, Type B, Type C, and with evolving generation, the data rates has been increasing, right? And the reason is because we have been able to pack in complex or denser modulation schemes, and the fact that we have been able to design faster and faster ADCs with a higher resolution. And here you can have ADCs sampling at hundreds of gigabits per second. And every time you make a file transfer through USB or LAN, ADCs are operated in parallel. So again, the point is, if you take your phone, it houses a whole lot of ADCs, and the specs are all broadly different, right? For example, the specs for a touchscreen ADC, they'll have a very high resolution, but the bandwidth will be very small. Now, if you come to a radio receiver, it will have a medium resolution but relatively high speeds. And when you come to your serial links like USB or LAN, it will be ultra high speeds but really low resolution. Okay. And I mean, not just mobile phones, right? I mean, if you go for any health monitoring system, sorry, resolution, I mean the number of bits. We will come to that later. Yeah, so let's say you take thermometer, digital thermometer, right? It gives a digital reading. Why? Because it has an ADC in the background. Now you have smartwatches that can detect every kind of biosignal and gives a digital reading, right? Again, there are a whole bunch of ADCs operating in parallel to give that, right? So yeah, next time remember that when you're opening Netflix and watching something, the moment you're touching your phone, an ADC is operating. The moment you're connected to Wi-Fi, a whole bunch of ADCs are processing signals. Right? So, yeah. So now that we have established ADCs are sort of around us everywhere, let's get straight to the course. So let's start with the first topic. So again, as you know, the first operation in digitizing a signal is sampling. So let's start with sampling. I'm sure you guys have learnt about sampling, so this is supposed to be a refresher. So sampling basically takes continuous time signal, say x of t, and after you sample you get a discrete time sequence x of n, that's all. And it's assumed that you are sampling it at uniform time instant spaced at ts, so right. So if you have signal like this, after sampling you take only discrete time points like this, so great. So let's understand this in frequency domain also. And for that I'll try to model sampling operation mathematically. And by the way, how is sampling modeled mathematically? Multiplication by a train of impulses, right? So if you have a signal x of t, the idea is you multiply it by a train of impulses. Say I'll call it some t delta of t. This delta of t minus ds, right? So in time domain, let's say you had something like this. So this will be a periodic train of impulses. Let's say this is 0 minus ts. So the output is going to be a signal. So let me mark this here. So we'll have something like this. Let me call this some x delta of t. Now this x delta of t, is it a continuous time signal or a discrete time signal? Okay, I mean, see, remember, discrete in time simply means that the signal is not defined for any other time instant. It is only defined at specific time instance. But here, what is the axis here? Here it is t. Here it is t. Here also it's continuous time. Yes. I mean, the moment I have t, it's a continuous variable, right? So this is still a continuous time signal. So of course, to get the sequence, which is a discrete time sequence like this, to be really accurate, you need to have something here, mathematically speaking, that takes in this continuous time impulses and puts out discrete time impulses like this. Again, this is just a mathematical modeling. That's not simply how it's done in practice, right? In practice, you just look at the signal value at specific time instance and just done. This is just for the sake of modeling. So let's now look at the spectrum. So let's say this guy, the continuous time Fourier transform of this is something like this. Say from minus b to plus b, this is 0. What is the Fourier transform of a periodic train of impulse? It's again a periodic train of impulses, right? And it's scaled by 1 by Ts. I'll not go into the details, you can work it out. It's n times Fs, where Fs is 1 over Ts, okay? Fine. So if I plot the spectrum, it's again will again be a train of impulses like this. I'll just mark a couple of them. So in time domain, these two multiply to get the signal. So what happens in frequency domain? It just simply convolves. So if I convolve these two, what do I get? I'm sure everyone is fine, right? I mean, basically, if you convolve this with a train of impulse, you are going to have shifted copies of the same signal around that frequencies where the impulses are located. Fine. So you'll have something like this. It will be scaled by 1 by Ts. So this is 0. Okay. So this is basically x delta of f. So now let's say I'm interested to find the discrete time Fourier transform of this discrete time sequence. So let's quickly see how we'll do that. So let me go to next page. So let's say I have the sequence x of n. I call the discrete time Fourier transform of say xd of e power j omega. How will I compute? I mean, if I have a sequence x of n, how will I find the discrete time Fourier transform? X of n. Okay, fine, great. And remember that our goal is to find the spectrum, from the spectrum of x delta of f. We already have this guy, spectrum of this signal. We are trying to find what is the spectrum of this. That's all, right? And I'll write this x delta of t in a slightly different way. So x delta of t is basically x of t times the periodic train of impulses. So if I multiply, if I take this x of t inside the summation, what do I get? Fine. Right. So this is now x delta of t. So if I were to write x delta of f, the Fourier transform of this signal, what will it be? No. I mean, yeah, that's what we got here, right? I mean, we already got it as like this. I'm trying to find out another expression for this from here. Okay. See here, if you see, the signal is basically what? A bunch of impulses, but with different areas, right? So Fourier transform is linear operation, so I can take it in x of nts is a scaling factor. Now I just need the Fourier transform of this guy. What is the Fourier transform of shifted impulse? Yeah, it's just e power minus j 2 pi f. It's all. This is same as the signal. This is same as the spectrum we derived earlier, but this is in a different format. That's all. So now, if you compare these two, things might become apparent. So we already have the spectrum of this. We are interested to find this guy. So if you compare these two, what do you think I should do to get the discrete spectrum? I mean, if you see, the only difference is, I mean, x of n is x of nts, there is no doubt. Yeah, omega should be replaced by this guy, right? Right side I have omega n, left side I have 2 pi f nts, so I'll replace omega, or the other way is I'll replace 2 pi f ts by omega. Right? I mean, it's the same thing you guys know, right? If you have a continuous time frequency f, when you sample it at a frequency fs, the resulting discrete time signal will have a frequency which is 2 pi f by fs. The same thing again and again. So, okay, so let's get some values. If continuous time frequency is 0, what is the corresponding discrete time frequency? If it is fs, fs corresponds to 2 pi, fs by 2 is pi, so on, right? Great. So again, the only thing we have to do is, in this spectrum, we just have to replace the frequency axis by our omega, that's all. Just changing the frequency axis, nothing else, right? So let's draw that quickly. Hold on. So this is f, this is x delta of f, this is scale by 1 by ts. So the discrete time Fourier transform is going to be same, nothing changes in amplitude, so only the frequency will scale. So fs corresponds to what frequency in discrete time? 2 pi. So this is my xd of e power j omega, right? And it's the same old, right? I mean, you know, discrete time Fourier transform is periodic with 2 pi. Okay. Cool. So now we are at this. Let's reprove the obvious. So let us say I now let me push it down first. Yeah. So let us say here I reduce the sampling rate fs. I keep reducing the sampling rate fs. What will happen? So these replicas will start to come closer, and beyond the point, what will happen? Yeah. So they'll start to overlap like this, and the signal gets corrupted, and the technical name is called aliasing. So we'll come to that. So let's say if I call this minus b and plus b, what is this frequency? Fs minus b, right? So to prevent aliasing, of course, you know, fs minus b should be greater than b. So this is what Nyquist told us centuries ago, or maybe decades ago. And this frequency, which is twice the signal bandwidth, is often called the Nyquist rate. That's basically the minimum frequency at which Nyquist recommended us to sample any signal, right? Great. So, okay, now let's look at the same effect in time domain also quickly. So I'll take some signal x of t, which is say cos 2 pi delta f t. Let's say delta f is very small, and I'm sampling it at fs, which is much greater than delta f. What will be the discrete time sequence I get? Yeah, basically when I'm sampling it, I'm just replacing the time by nts, that's all, right? So this is basically cos 2 pi delta f, I am taking the values at NTS and I'll just write it as n by fs. Fine. I mean, this again boils down to same thing, right? I have a continuous time frequency delta f. After sampling at fs, it results in a sinusoid in discrete time at a frequency 2 pi delta f by fs. Fine. Cool. So now let us say I have another signal, say cos 2 pi fs plus delta ft. I sample it at fs. What will be the resulting sequence? You'll get the same. Is that okay? You can work out the same thing, right? You can replace, t by n by fs, and you will still end up with the same sequence. Is that okay to everyone? Right? I mean, this is basically the issue of which one? This one. This fs, right? Here, that's. I mean, that just. I'm just mentioning the rate at which it is sampled. It's okay. It's just for under it's. You can either put TS or FS, doesn't matter. So this is the issue of aliasing, where if you don't sample it fast enough, a high frequency signal may look like it is a low frequency signal after sampling. So cool. So now if I sample at a frequency fs, what is the maximum frequency that can be sampled without encountering aliasing? Fs by 2. Is that okay? So maximum frequency is fs by 2. So let us say now we have a signal, a sinusoid at fs by 2 plus delta f. This is beyond the maximum frequency. I mean, that will not result in aliasing. So if I sample it at fs, will there be aliasing or not? Sorry? No, okay. I'm just saying. See, let me re-walk you through the argument. See, if I have a sampling rate of fs, so max frequency that can be sampled without causing aliasing, what is that? Is that fine? I mean, it's just, inverse of converse of Nyquist sampling theorem, right? So I can sample a frequency of fs by 2 maximum without resulting in aliasing. So my question is now, let's say I take a sinusoid at a frequency fs by 2 plus delta f. I am sampling it at fs. Will this result in aliasing? Yes. So what will be the frequency to which it will alias to? Okay, multiple options. No, fs by 2 plus or minus cannot be the case, right? Fs by 2 plus is fs by 2 plus delta f is aliasing. See, when I say if it aliases, it should alias to some frequency less than fs by 2, right?
Minus fs by 2 plus delta.
Yeah. So again, you can work it out. I'll just give the way to think is, see, this frequency, when you sample it at fs, will result in some discrete time frequency omega. Now if I take the same frequency, I do plus or minus fs. If I sample it at fs, I'll get the same omega, right? So if I just take minus fs here, and this basically simplifies to what? Fine. Of course, real signals will have equal content in the positive frequency and negative frequency. So this basically fs by 2 minus delta f. Fine. So basically, if you are sampling at a rate fs, let's say fs by 2 here, this. So any frequency or this range of frequencies from fs by 2 to fs, it will alias back here, right? So this frequency fs by 2 plus delta f is going to fall back here to fs by 2 minus delta f. Yeah, that's what I'm saying, right? It's a negative frequency, but real signals will have same content and both positive and negative frequencies. Yeah. Is that okay? So, I mean, by the same, sorry? Okay. Is this point clear? Is this point clear that if you have a tone at fs by 2 plus delta f, when you sample it at fs, it will alias back to fs by 2 minus delta f. Is that point clear or not? Okay. You can work it out. I mean, I'm just giving a simple explanation. See, let's say fs by 2 plus delta f. When you sample it at fs, you will get some discrete time frequency omega. What I'm saying is, even if I add or subtract fs from that, I'll get the same frequency omega, because that's what we saw here, right? Isn't it? So if I subtract fs, I'm going to get the same. So that results in delta f minus fs by 2. And it's a negative frequency, so you should have a positive counterpart, and that is fs by 2 minus delta f. Fine? So if that's what is generalized here. So if you have a tone at fs by 2 plus delta f, after sampling it will fall back here to the left side, the same spacing. I'm sure you know, right? If you have a tone at fs, when you sample it at fs, what is the frequency to which it will alias to? If you have a sinusoid at fs, you sample it at the same rate fs, what is the frequency it will alias back to? 0, right? I mean, you can see from here, right? I mean, fs will fall to 0. I mean, other thing is, I mean, you can see in time domain. So this is exactly like this. This is a sinusoid at fs. You sample it fs, you will get a constant DC signal. Right? Cool. So probably I can show some examples. So yeah. So this is an example where I have strictly obeyed Nyquist condition. So I think the sampling rate is 10 Hertz, and I think my input is 1 Hertz. So the yellow curve you see, that is the continuous time signal, and the blue dots are the discrete time instants that have been sampled. And it seems like it's not an issue. Now, of course, I'm taking the another case where the sampling rate is same, but this time my input frequency is, I think, 11 Hertz. So fs is 10 Hertz, fin is 11 Hertz. So what will be the frequency to which it will alias back to? 11 Hertz signal sampled at 10 Hertz will alias back to 1 Hertz, and that's what you see, right? I mean, the yellow curve is the 11 Hertz signal. I'm sampling it at 10 Hertz, and the blue dots are the like sample points, and it looks like it is of a low frequency sinusoid. And the period is also, you see, it's 1 second, 1 Hertz. So this is another extreme case of aliasing, where I think again fs is 10. I think my fin was 111 Hertz. So again, what is the frequency to which it will alias back to? 1 Hertz. Is that okay? So it will also alias back to 1 Hertz. So again, that's what you see here. A sinusoid with a period of 1 Hertz. And of course, a more cool demo of aliasing is in photography, right? I mean, you would have seen cases where the rotors of the helicopter doesn't move at all, or you might have seen videos where of water dropping from a tap, where it looks like the droplets are moving up. I mean, there's the same thing, because basically if you have a tap, water droplets are falling down. Videos basically samples of multiple images played at some rate, right? If you don't sample it, if you don't capture that fast enough, it will look like first, this droplet is falling, and then you might capture an instant where the droplets are here, right? So it will look like as though the water is moving up. Other thing is the fan, right? If you try to capture the motion of a fan or helicopter rotor using a camera, and if you make sure that the speed of the fan and the frame rate is synced, it will appear as though the fan is not moving at all, right? Basically, the moment it completes one rotation like this, you take one snapshot here, another snapshot here, another snapshot here. So a fast moving signal, it will appear as though it's not moving at all. Huh? Yeah. Cool. So that is clear. So let's look at this. So let's say now we have, this is the frequency axis. Let's say this is minus B to plus B. Let's say this is Fs. Yeah, okay. Let's say I'm sampling a signal at rate Fs. And let's say I'm interested in a band of frequencies from minus B to plus B, right? So the question is, what is the minimum frequency? I mean, of course, let's say now the input has all frequencies, okay? When I am going to sample it, I'm sure that there will be aliasing because input has all frequencies. What is the minimum frequency which can potentially alias back to this band? It's greater than Fs by 2, but what is the exact, I mean, assume that Fs is much more greater than B, right? I mean 2B for simplicity, right? You can maybe draw it in a more realistic way. Let's say B. Okay, why did you say that? I mean, yeah. Very good. Yeah, I mean, see, I'm sure, what happened? Everyone knows that if I have a frequency at Fs, if I sample at Fs, where it will alias to? 0, right? Now, I wrote it inverse, hold on, this is plus B minus B. So here if I go to the left of it, what is the minimum frequency which will alias back, right? So Fs is going to come here, any frequency here will go here, and the minimum frequency is basically Fs minus B. Fs minus B will fall back here, right? Any frequency here is not a problem. From B to Fs minus B is not an issue because it is not aliasing back to your frequency range of interest. They are also getting aliased for sure, but our goal is to see if they are getting aliased in the required band of frequencies, which will not happen. Is that point clear? So this band of frequencies from around Fs with a bandwidth of 2B. So this band is what will alias back here. Bandwidth. Sorry, yeah? Yeah, see, technically speaking it's minus B, but for real signals, minus B or plus B doesn't make a difference. I mean, even there, if you recollect, it was, I think, delta F minus Fs by 2. But the logic was, for real signals, negative frequency is same as positive frequency, right? I mean, cos of minus F is cos F, sin of minus F is minus sin F, just a phase shift. The frequency is same. So it could be a band of interest. Let's say I'm looking at, this is the bandwidth which is of interest to me. Is this point clear? So if you are interested in a band of frequencies from minus B to B, frequencies around Fs will what will alias back, and that band is Fs minus B to Fs plus B, right? Similarly, it will not stop at Fs, right? Even from around 2Fs, this band will fall here, and so on. So, that you can work out, right? It will not obviously fall here, but it will alias somewhere else. That you can work out. Okay. Great. So this is clear. So let's say here when this lecture is getting recorded, we are recording basically an audio signal, right? What is the maximum frequency or bandwidth of an audio signal? Let's say 20-24 kilohertz. So let's say obey Nyquist condition and sample it at say 50 kilohertz. So if I directly take the signal and sample it, will it work or do you foresee any issues? Yeah, I mean, we just saw, right? Your signal might be band limited to, let's say, the required bandwidth. But when you're sampling the signal, it is not just the signal alone. You will have all sorts of stray signals. If not, you will have electronic thermal noise, which is omnipresent at all frequencies for us. So, by the same logic, so this band of frequencies around Fs, 2Fs, 3Fs, everything will sort of alias back, right? And after sampling, what you will see is, you will have signal of course, but it will completely get drowned in noise, right? You will not be able to recognize the signal at all because you have aliased so much of noise that the noise is dominating the signal. Is that point okay?
So why will 2Fs signal alias back to in the band?
Okay, so if I have a sinusoid at 2 Fs, if I sample it at Fs, where will it alias back to? Yeah. So I mean, you can, if you are confused, you can always do this, right? Cos 2 pi. This is the signal. I am sampling it at Fs. Where is it getting alias back to? DC, right? I mean, whatever happens at Fs, Fs is not some some pure number, right? Multiples of Fs also have the same property.
When you're sampling this, pi will be there at Fs also 2Fs also, right?
Yeah.
That will also alias.
No, but see, the actual signal is only this. Analog signal is this. See, your analog signal has a band limited spectrum like this. It is only after sample you will have the replicas.
When it will alias back also, right?
No. When you, after sampling only you have that, right? See, you have continuous time signal. Sorry, hold on. See, your continuous time signal is band limited to -B to B.
Yes. This is like input.
Input, right? When you sample it, you will have the replicas,
Yes.
right? Now the thing is, along with the input, you will have noise, right? And the noise will also get aliased here. That's all, right? So we'll have, I mean, it's not a rectangle. You will have,
Straight line.
yeah, you will have a complete noise like this. I mean, remember that after sampling, the spectrum is periodic from in a discrete frequency range 0 to 2 pi or minus pi to pi, or from minus Fs by 2 to plus Fs by 2, if you are looking at continuous time frequencies. So whatever spectrum you have, that's just going to repeat. Is this clear? So if you directly sample the signal, noise from multiples of Fs, from around multiples of Fs, they will alias back to your required signal band and it will drown out your signal. So what is the solution to this? Yeah. I mean, see, noise is present along with your signal. The issue is because your signal is nicely band limited, but when you're sampling at Fs, you're allowing signals from higher frequencies to alias back. So what can you do? Right? Is that point clear? My signal is anyways band limited to -B to B. The issue is because noise from higher frequencies are falling. I'll just filter it off in the analog domain. Right? So before sampling, you always have to have a low pass filter. In this case, a low pass filter.
That means you are removing the noise from the
High frequencies. And this is often called the anti-alias filter for obvious reasons. Fine. So sampling is always preceded by a low pass filter or a relevant filter to make sure you filter out all the things that can alias back. Okay, cool. So now let's look at some. Yeah. So let's say again my band of frequencies of interest is minus B to plus B. This is Fs. So the anti-alias filter, which is a low pass filter in our case, let's look at how its characteristics should be. What is the range of frequencies it should completely pass? Right? So it should have a flat response till this, and it should provide sufficient attenuation to anything that will alias back. And what is the minimum frequency which can alias back here? Yeah, Fs minus B. This is the minimum frequency which can potentially alias back into my band of interest. So my low pass filter must provide sufficient attenuation to this. So it probably should have something like this. Okay.
Should not end at Fs minus B.
I mean, it's a frequency. I mean, it's a low pass filter, right? Its frequency response will be there forever, right? I mean, you should make sure that this should be at least attenuated by a sufficient amount. If this is attenuated by sufficient amount, all the other bands will also be sufficiently attenuated. Great. So now let us say I strictly obey Nyquist because Nyquist was a smart guy. So I choose Fs to be 2 times B. So this is F minus B to B. So here the band of frequencies which can alias back is Fs minus B to Fs plus B, right? If I choose Fs to be 2 times B, what is the band that will alias back? Of course, the low pass filter must allow this. B to B, right? So basically I need to filter off anything beyond B. So the characteristics, how should it look like? It should basically drop immediately. So do you think it's reasonable to realize a filter like this? No, okay. I mean any kind of time response or frequency response which has a sharp jumps like this, it is impossible to realize, right? So now if you are a designer and you are asked to do this, how will you choose your sampling frequency to be? Is the point clear? So again, the logic is this: I need to make sure the response is flat till B, that I cannot avoid at all. What I can control is the attenuation, the frequency at which I should have the attenuation, and that depends on Fs. So if I make sure this frequency which has to be attenuated and the frequency which has to be completely passed, they are far apart, I am good. And that is possible if Fs minus B is greater than B. So in practice, you always exceed Nyquist expectations and sample beyond 2B. And this is often called oversampling. Okay. And this ratio of the actual sampling rate to the Nyquist sampling rate, which is 2 times the bandwidth, that's abbreviated as OSR for oversampling ratio. Okay. And in practice, we usually choose this OSR to be in the range of 2 to 4, simply because it makes the filter design easier. Okay. And of course, there is another class of ADCs called noise shaping ADCs, where this oversampling is exploited for something else, and there this OSR could range anywhere from 200 to 500 or even more. But there the goal is to not make the filter design easier. There the use of oversampling is for some other purpose, we'll see later in the course. But the bottom line is it is always oversampled in practice. Okay. Great. So bottom line, before sampling you have an anti-alias filter, and to make sure the design of the filter becomes practically possible, you make sure you oversample beyond the Nyquist recommended sampling rate. Okay, great. So now we have seen sampling, that is how we can convert continuous to discrete time. Let's quickly look at the inverse operation also, how you can reconstruct from the samples. And for that, first let me draw the block diagram of, or the mathematical model for this sampling. So first, of course, we have our low pass filter, and then we sample. So I'll again write them, sorry, we'll have it, I'll probably discuss it later, yeah. So again, the sampling I'm modeling as multiplication with a train of impulses, and then some block that puts out discrete impulses from continuous time impulses, right? So time domain, let's say this is the signal. Here I'll have something like this. Right, this is T, this is T. And let me also draw the spectrum now. So this is the band limited spectrum of the input signal. So after multiplication with impulse train, I'll have this replicas. And discrete spectrum is the scaled version of it, I'm not drawing. So this is the, so now let us say I have only the samples here, discrete samples.
When we do this scaling, is that by x-axis gets scaled, right? Not by x.
No, yeah, y-axis doesn't scale. So now let's say the goal is to get this continuous time signal x of t from the discrete time sequence x of n, right? So again, see here we went this way, so logically it makes sense we should somehow go this way. So I have the discrete time impulses. So let's say mathematically I have some block. Oops, sorry, I have to draw again. So I have the discrete time impulses. So let's say mathematically I have some block which puts out these continuous time impulses. This step is done, right? And
Scaling, right?
I mean, in frequency it's scaling. I'm just saying mathematically it's some operation that takes in discrete time impulses and puts out continuous time impulses. And this has a spectrum which looks like this. I finally want to get this signal which has a spectrum like this. What should I do? I just need to put a low pass filter. So that will extract only this guy. Fine? So this is basically a low pass filter. Of course, this is not how we'll do in practice. I will quickly show how the reconstruction happens in practice, but this is the mathematical model. Again, it's just the inverse of this guy, right? This chain is inverted here, that's all. So, of course, in practice, what we do is this. So, let me show here. So, let's say these are the discrete impulses. When we are reconstructing, all we are trying to do is fill in the blanks, right? We are trying to make sure, and we are trying to somehow make sure the gap between this is filled based on these samples. That's all, right? And let's say if you are very lazy, what is the simplest way in which you will fill this gap? I know this value at this time instant is this, right? I want to fill the space from here to here. Zero is, let's say you are not adding any information, right? Let's say you want to do something better.
Same.
Basically you try to do the same, right? So it seems like the lazy and simplest thing to do. So, sorry, hold on. Yeah, if this is a sample for one period, I'll hold the sample. Similarly, I'll hold the next sample for one more clock cycle and I'll do this. Okay, and this is called zero order hold. Simply because it pays, it pays zero respect to what samples are before or after. It doesn't care what is before or after. I'll just look at the current sample, I'll hold it. Of course, there are higher order holds which will take into account all the past samples, but this is the simplest thing to do and it is done. And if we were to model this operation, let's see how we will do that. So again, I have discrete time impulses. So let's say I have a mathematical block which puts out continuous time impulses. So after this, I'm doing something. So I'm doing something here to get this kind of a staircase waveform, right? So what is being done? If I have to model it mathematically, I mean, I'm trying to model this operation mathematically, right? So let's say first I got the continuous time impulses from discrete time impulses. Next I'm doing something on these impulses to get this kind of staircase approximation. So what is that operation? Okay, I mean, don't think too much, right? I mean, see, this is the impulse. In response to this impulse, what is the output from this waveform? It is basically this. Similarly, in response to this impulse, the response is this rectangle. So essentially, a filter whose impulse response is what? If I have an impulse, see, if I give an impulse here, the response of the filter is this. So what is the impulse response? It's not integration. I mean, you can think it's an impulse response like this, 0 to ts. Fine. This is h of t. Right? That fine? Okay. And I mean, if you see before, for reconstruction, what we wanted was after this guy, we need to have an ideal low pass filter. But here we seem to have something which is not a great low pass filter, and that's why you are not getting the smooth waveform, right? Where had this been an ideal low pass filter, we would have gotten it. But of course, this is much easier to do, so we'll first start with this, and then we can have a much better low pass filter here. Just push it down. So the zero order hold is easy to do, and after this you can put any low pass filter and smoothen the waveform out.
Okay.
This is what, right? I mean, see, you already know the spectrum of this guy. So this spectrum, I mean, this waveform is getting filtered by a filter with this impulse response.
What is the frequency response?
That you should find, right? It will be a sink. You know the impulse response is rectangle, frequency response it will be sink. So basically, see, ideally you want a low pass filter whose frequency response look like this. But now you are having a low pass filter whose frequency response is sink. Right? That's why you are not able to get a smooth waveform. Instead, you are getting this kind of staircase approximation. I mean, even logically, see, if I were to get a smooth waveform here, right? I need to have information about all the past samples, right? Only then I can smoothen the waveform out. Without any information, with information on only the current sample, I can only do this. If I have more information of the past samples, I can do some more processing and smoothen the waveform, right? And basically, if I have information of more and more past samples, I can do a better job. And that simply means I should have a low pass filter with a higher order. See, a filter with the higher order simply means it takes into account the effect of signals which came much before. Basically, the time output at that time instant depends on input that came several time instants before, right? And as you keep increasing the order, the memory of the filter also increases. And if you have a longer memory, you'll have more information about the signal and you can smoothen the waveform better. That's it.
So
there are two parts using useful reconstruction. One is the impulse response and other is the low pass.
No, impulse response, I mean, this is also a low pass filter, right? This is the impulse response of that low pass filter. See, impulse response is defined for any system, and the system is, I mean, system with this impulse response indeed is a low pass filter, but not a great low pass filter.
So what is the useful, I mean, what is the use of doing two low pass filters?
See, the idea is doing this is easier first. From the samples, reconstructing this waveform is easier, right? I mean, it is not easy to generate impulses, right? So it's easier to hold the sample and then you filter it later. And I can show some examples here. So again, the yellow waveform is a continuous time signal. The blue ones are the discrete samples. So in the first stage, I sort of do the zero order hold, where I hold the data for one whole sampling period. And then I sort of do a filtering on top of it. And once I filter the zero order hold waveform, the white is the smoothened curve, right? And you sort of get the original signal back. Okay. Yeah, it will be, right? I mean, filters are causal filters. So if you give some input, it will take some time to respond. Great. So, yeah.
Zero volt is cascaded very high. If it is cascaded the zero volt or then effectively that whole system becomes a higher order.
Exactly, yeah. Okay, so some time is there, so let's quickly move to the next thing, which is after sampling, what do we have to do? We have to quantize, so let's look at quantization. Yeah, I mean,
It is like it requires infinite memory. But let's say I have that ability, and even then, is it possible?
you can do. In fact, sharper roll-offs can be achieved in digital filters easier than in analog filters. That's simply because you can have, you know, a long memory in digital, and then you can do it.
So I used to think that a sharp filter means square kind of this square kind of this response.
Correct.
Means that it should in the time domain its response will have in the time domain its impulse response will have more negative time content and positive time. That's simply not possible because then it becomes anti-alias.
Yeah, then you can shift it, right? See, instead of having a response like this, see, now you're looking only at the magnitude response, right? This is the, let's say, thing you want. You can have a sufficient phase, this is only the magnitude, isn't it? You can have a phase which is sufficiently delayed and then get it. Infinite, of course, it's not possible.
That is what I'm saying. Even with this big wall kind of response, the time domain response will have again negative time.
Correct.
Positive time. But that is not possible.
Yeah, that's why in practice it will be shifted, right? You will have causal things, will have the phase shift to be positive. We'll discuss it later. Anyway, so let's start with quantization. So as we saw, quantization is simply doing the discretization in the amplitude axis. That's all. So let's say this is my input amplitude. Say it's ranging from, say, a minus reference voltage to a plus reference voltage. The goal is to discretize this axis. So I'll take a range of amplitude. Say I'll scale it to -1 to 1 for simplicity. Say I'll take a range -1 to, say, -0.75. I'll say any amplitude falling in this range, I'll assign some fixed amplitude number. And what do you think is a reasonable amplitude to assign? No, I mean, if for an amplitude in -1 to -0.75 range, if I were to round off that number, I mean, this is basically a rounding off, right? Any number in the range of -0.75 to -1, I'm rounding off to some number. What is a reasonable number to round it off to? Half of that range. Fine? So I'll keep doing it for all, the entire thing and do it. This is essentially quantization, and of course the moment you do it, you'll have finite number of amplitude levels, and then you can encode them using binary bits, right? If you have n bits, you can have 2 power n possible levels, and you can do it. So let's quickly look at the characteristics of quantizer. So let's say the input is y, the output is v, and the mnemonic is c. The quantizer is basically rounding off, right? It is basically making some error. So you can think of the input y, when it's rounding off, when it's getting rounded off, its tail gets chopped off, we get v. To remember, right? So great. So now let's say again the input is ranging from minus vref to say a plus vref, and let's say I want a total of 8 levels. That is, I want to divide the range of input amplitudes into total of 8 levels. So basically 1, 2, 3, 4. The negative axis again 4. Right? Oops, sorry, disappearing pen. So what do you think is the width of this? Huh? No, it's not. 2 vref divided into 8. Right? So often this is called the step size or delta. So in this case it is the range which is 2 vref by 8, and if you have total of L levels, it's 2 vref by total number of levels. That's all, right? So again, for simplicity, what I'll do, I'll scale this by delta. I'll say it's 1 delta, 2 delta, 3 delta, 4 delta. So similarly, it's minus 1, minus 2, minus 3, minus 4, right? Input, yes. So again, we are going to round off. So any any amplitude in this range 0 to 1 delta, what will I round it off to? Delta by 2, so 0.5. So let's say I round it off to 0.5, which is say here. Similarly, in the negative side, 0 to minus 1, and round it off to minus half. Fine. Here. And then I'll do that for all amplitudes, right? So, okay. Great. So, yeah, one more jargon. So this entire range of minus vref to plus vref, that's called the full scale range. Okay. Yeah, and now we have 8 levels, so we can encode them using how many bits? 8 levels, 3 bits, right? So we can just say 0, 0, 0, 0, 0, 1, and so on, right? Blah blah blah. And this step size delta is also called as LSB size. LSB is least significant bit. I mean, simply because if you want to change the LSB by 1 bit, at the most I have to change the input amplitude by 1 delta, right? Great. And yeah, so it turns out this is not the only way in which you can have the quantizer characteristic. See here, if you look at it, the 0 or the middle of that full scale range kind of lies in this transition point, right? But I can also choose the characteristics in such a way that the 0 lies in the flat region. That is also another possibility. So this kind of quantizer characteristic, which has a rise in the middle of the characteristic, is called mid-rise. So we'll have the other thing which is called mid-thread, wherein you make sure that around 0 it's constant. So here we'll say from say minus delta by 2 to plus delta by 2 0, and then you sort of keep doing it.
There is a jump at the big point.
Sorry, this?
There is a jump at 0.
Correct. Yeah. So I mean there are a couple of differences, not significant. So one is, you see that if your input amplitude is close to 0, right? If it's very close to 0, what will be the output here? It will be 0. And if the input if the input is again varying close to 0, what will be the output here? I mean, let's say it's small, right? Around 0, it's varying by a small amount. What will happen? It will sort of toggle between, So, I mean, if you want to have a clean output for low signals, you might probably want to do this. Else, this is better. And other thing is, see, here if you want to have in this mid-rate quantizer, if you have a symmetric characteristics, I should have an odd number of levels, right? Here, see, I have 3, 4, 5, 6, 7. Because 0 is one of the levels, I should have, same number of levels on positive and negative, so you'll have total of odd. Whereas here I can get a symmetric thing with 8 even number of levels, a minor difference. Okay. And unlike sampling, and before, by the way, we looked at sampling, right? Is sampling a linear operation or a non-linear operation? Huh? When is an operation on? Sorry. Okay. When is this operation linear? I mean, let's say, see, what is the condition for linearity? And something else, right? For 0 input, I should have 0 output, homogeneity. And if I scale the input, output should also scale. If I have a 0 input, when I sample it, will the output be 0? 0. If I have some input and scale that input, after sampling, will the sampled output also scale? So it's linear or non-linear? It's a linear. Sorry? Sampling is not like, sampling is linear, but the thing is, it is not time variant. No, sampling doesn't involve convolution. Sampling doesn't involve convolution. It convolves in the frequency domain, but we are looking at the operations are all in time domain, right? So sampling is a linear operation.
So what if we take two analog two signals? First one has magnitude 0.2 and another one has magnitude 1.2. And they are like quantizing it.
No, not talking about quantization, right? It's sampling alone. This sampling is linear, right? But of course, quantization is not linear, like is pointing out, right? You can see if I have some input, I get this output. I scale the input to this value, the output doesn't change. And obviously, because of all these jumps, it's non-linear, right? So it's very difficult to analyze. So in the next class, we'll see how we go about analyzing or understanding quantization. So let's stop here. Oh, I didn't record. Oh, record.